Hi, everybody. This is the second presentation regarding to our radar fundamentals training series. And the topic is the radar signal processing pipeline. It's a very short summary of the whole process. Since it's a very, it could be very complicated with so many materials. So we will not be covering everything, but the whole idea is going to be to talk about the main blocks. And as I said before, this is going to be part of our knowledge repository, which will come with technical report and video, and also the reference articles. Let me just turn myself off. So we will have complete text information on each page. So it's going to be like an audiobook. It will be different from a general presentation. Scope is going to be limited to sensor engineering. And for the people who are following this through video in MP4, please stop the video and go to references for more details. You can go back and forth whenever necessary. And if anybody have any questions, suggestions, any request, you can contact us, Shirvasan and myself. And here is the keywords for reference. And for this course, we will be using some of the prerequisites, and in the future, all of them will be ready for our engineers as a separate presentation. And we will ask them to follow these videos before coming back to this. So here we go. Radar is range detection and ranging. And it started at World War II by Russia and Germany and Britain, right in the beginning of the war, and it had certain effects in the history. The main purpose is to measure distance, target direction, brightness, velocity, and much more. Depends on the application. And as a radar engineer or an engineer who's post-processing our radar data, we all must know, I mean, this figure is illustrating it, what the characteristic parameters of a radar system are, the reasons behind those parameter settings, their pros and cons, and finally the performance metrics and the performance parameter values, which are directly related to those radar design values. So as you can see, the whole waveform, shape, and all of the parameters directly affect on the performance, and it has to be optimized and designed accordingly to the application. So when you talk about design, radar system design starts with determining the scope and the requirements of any system development, and radar system design efforts involve parameter settings, as I said before, which often have contradicting outcomes and which need some level of optimization. Like if you want to improve some range value, then you might be losing on Doppler. And we will see those in couple minutes. And there in the figures, you see the effect of just how directly impacts the radar software and hardware design efforts, depending on the waveform. On left, you have pulse Doppler, right? You have the FMCV, frequency modulated continuous wave radar. And that is what we're gonna examine in this presentation. So here you can see a very classical radar waveform. You have the TX on, which sends a pulse. Then it turns off. You listen, you record what's coming back. You could call it the signal return, or you could call it the echo. And today, this radar waveform can be implemented by not just a simple complex exponential as shown in the figure that goes way back to the beginning of World II era. Today, we have very complicated waveforms. Here on the figure, you can see stepped frequency. It's a hopping frequency radar. You can have the chirps. You can have each pulse as a frequency chirp, or as shown in this figure, you can have digitally coded continuous wave signals, where the signal is like a communication signal. It has some modulation on it. Here you have a phase shift keying waveform, and it's binary. So the phase is +1 or -1. So it means 0 and 1 in digital communications. But here it's just a code. It codes the radar signal. And then what you do is then you send this transmitted pulses. And then if radar is turned off, then your receiver is recording what's coming back. And here you see how a transmitted radar pulse is reflected by, in this case, just a single target, and it's creating a delayed version of the original signal. So since we are the ones who are sending our transmitted signal, we know what to expect. The reflected signal should be very similar to what we sent. So it's a delayed version of the pulse. It's an echo, very similar to in audio. When you yell to a mountain side, you can hear yourself as is on a delayed version. So here, again, transmitter is on and off, on and off. You're sending pulse and recording the reflections, the echoes, and as part of the design, transmitted signal is sent. But here, we often don't see in the books or in any figure that I need to underline this. You know, look at the figure. You have the transmitter and you have the received signal, but in reality, the figure is very much different. And normally, we don't see figures like this on an actual in a case, because transmitter signal is huge when you compare with the very, very weak received signals. So they're not comparable. And for example, for mobility and transportation applications, say we have a range of 200 meters, say, this ratio could be larger than 100 decibels. And 100 decibels means that 100,000. So you sent 100,000 unit of power, and then the received signal is just one. Nothing almost coming back. So it's very, very weak. So, and think about it. If you need the transmitter and the receiver to utilize the same antenna, or TX signal is highly coupled to the receiver, there, for example, for the monostatic, both circuits are very close to each other, then this huge signal definitely saturates the receiver, and the receiver is blinded by the strong TX signal. In these cases, you need to operate on a different time durations, and you transmit, you stop, and RX starts receiving the TX whenever TX shuts up. So that's how it goes. But depending on the antenna design, you might control the coupling between TX and RX. And then for these cases, that's the second case we could say, you keep your transmitter on all the time, RX on the time, all the time. Then, as part of the radar design, the transmitted signal, you need it to be coupled, because maybe you multiply the received signal with the transmitted signal in time using an analog mixer. That's a hardware design. Then we can have this continuous wave option. And here, I need to underline that TX is never off. And one question for the audience, I could, put here, just you to think about it. Can you compare these two cases where the minimum range and the range resolution by the end of this presentation? I hope you have some idea how to, calculate those in these two different cases where the TX is continuous or it's on and off. Let's go back to the other case. That's, for example, the radar Infineon and TX cases that we are working on. TX is switched on and off for the frequency modulated continuous waveform case. So far, we saw the first two dimensions of radar signal processing. So here you send a chirp, it goes, and then you record the reflections, and then you send it again. You send it again, second pulse, third pulse, until you go to the end. So here we are going to see there is two dimensions for the receivers to collect data. One axis is for the first chirp, and we call it the fast time. And once you start collecting the second pulse, third pulse, fifth, and then it goes on forever maybe, and you call it the slow time. We're going to come back to this. And let's see. We're going to come back to this. And the third dimension is where we have multiple antennas. We will collect signal from multiple antennas. So the first two sampling domains are fast and slow time domains. They're temporal. That's the function of time variable. And in this slide, we see the utilization of different transmitter and receivers. So sampling using different antenna terminals is taking place. And each antenna is located at a different position. The sampling here is called the spatial domain. So that's the space domain. So that's the third dimension that we're going to go into. Here I'm just defining it, and elements being different at different locations will allow us to estimate the direction of the targets. And so far, we completed the general terminology of what we're going to get into details. So here we go. That's radar signal processing is RSP, and I call it the classical because it was invented in the beginning of World War II, and nothing much changed actually. Today we're discussing the new technology using AI and artificial intelligence and machine learning. So time is changing, but this structure goes back to World War II. It's very old, and we have so many modifications and applications, but basically the idea is the same. So here, that's what we're going to go. So, and here on the figure, that's an example. That's a good old fully analog radar system. And in many military ships, you still see them operational. It works. And of course, here we don't see the huge antennas. It's not in the picture, but if you look at it, you can see the thick RF cables on the ceiling of the room. Those are, not just engineering, they call it the art. So next to this room, they have the transmitter room where you have large magnetrons operate, and they radiate very much. So the operators, generally, I like to share an experience is the operators in those huge ships and the people who work in the magnetron rooms, the transmitters, which they have megawatts, within the room. And what they say is the operators always have daughters. It's funny. They say they always have daughters. And during my time in those rooms, I had my daughter, and I'm very happy for that. So it's interesting. I don't know if it's true or not, but it's a very radiative environment. So coming back to today's radars, they're small, they're very high tech, and many of the processing is done on the digital domain. So even the idea is the same, but the implementation and the equipment, the electronics is totally changed. So here we see the basic blockchain of the pipeline. You have the transmitted signal transmitted on the left side from the antenna, and then it hits the target or many targets, and it comes back at the receiving antenna and later processed in steps. So linear low noise antenna, ADC, analog to digital converter, range processing, Doppler filter, angle beamforming. So this is what we are going to summarize today. The blockchain on the left side, on the right side, sorry. We will talk about what the data is, etc. So let's go. Normally you have the antenna signal processing is still done on the analog side, but the whole processing after ADC, range, Doppler, angle, can be done on a software reconfigurable hardware. And depends on the application, depends on the product. You have different solutions. And that's what we have here is the generic description of the RSP pipeline. On top figure, what you see, a famous F-16 fighter, multifunctional radar. And the radar is located at the nose. And on bottom, you see Infineon's $500 FMCV radar. One is millions of dollars, the other one is $500. And basically, they have the same blockchain. So implementation is super different. And they do have very similar processing in blocks, if you just look at it. So I worked in both of them, and I see many common steps. So all radars were analog in the past. Now we see mixed signal, both analog and digital processing. So here comes the first block. That is the ADC, analog to digital conversion. And right at the end of the antenna terminals, you have some filtering and signal conditioning, which is ignored here. Then you convert the whole thing into digital domain. So even the slide is similar. I have few words. So sampling on the fast time domain describes the sampling due to the single transmitted pulse. So you send a pulse and you receive it. You call it the fast time. This sample data is the true raw signal data for the radar. Input data is often called raw, even if it's not raw. We will discuss that too, because some other applications might call raw differently, but this is actually the raw signal. And samples do not carry any range velocity, angle, amplitude information yet. It's basically raw. It doesn't have any info. Generally, sampling starts immediately after TX shuts off, and it continues until the last sample coming from the furthest target is expected to arrive. So that's our mux. That is just before.
Gok,
Yeah.
just one. I think Benuraj has raised his hand.
Oh,
I'm
okay.
asking him to
Yeah,
mute.
go ahead.
Benuraj,
Yeah.
was it by mistake or?
Yes.
Oh, go
No,
ahead. Yeah.
no, 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 no. I have a question. Go. Thanks for explaining this. Can you move to the previous slide? I have one question. I'm sorry if I'm breaking the
Go
flow.
ahead.
That's why.
Yeah.
Yeah. So in the digital versus analog, right, or whatever you have measured from a deep learning perspective, or in fact, even in a classical method, right, wherein we used to before the deep learning era, wherein let's say using I think you have mentioned about also the PMCW
Yes.
is am I pronouncing correctly? Okay.
Yeah.
Even for that some of these classification, event classification, or somebody's breathing or fan is moving and things like that, which is pretty common in surveillance, were happening long time before all these deep learning things came in. So my question to you, when I saw the one which is blocked here in a red, are these some of the ways to derive feature, right? The time and frequency domain analysis, which is like a pre-processing even for a classical method of, let's say, classifying events, right? Are these the usual features that needs to be processed once you have given a radar signal? Is that statement correct, irrespective of what kind of radars it is?
Um, Let me, try to answer it. If not, you can,
Yeah,
revise the question.
sure,
So
sure.
once you get the data, you
Hmm.
have, we will see it. We're getting there. We will see fast
Okay,
time, slow time, and the channels, and that's going to be called the radar cube.
okay,
So in terms of AI, it's not human. So this idea, the whole process, range, Doppler, angle, works for us. We are the humans. So what you do, you send a transmitted signal and you look for the same signal. And you must have the range correlator to make this happen. And same,
okay,
you need to go for the Doppler filter because in both steps, what you basically do is you get rid of the noise and your target signal goes above the noise level. Then you
understood.
see where the targets are. Then you do the angle beamforming. This is a general summary.
General thing. So
Yeah,
so
but
I understand.
but
So
the thing is,
mm,
that was a project for I think 3 years ago. I was in a different company and
mm,
I worked with a team in MCW. And what I tried was using AI to get rid of data without any filters, without any
okay,
angle beamforming, nothing. And there we were not able to get a good result for some
okay,
reason. Maybe we didn't do a good job. So what we did was we processed range and Doppler to support the data and create a better training data set so that we were able to get good results. But again, it takes time and we didn't have the
understood.
time, so we couldn't continue.
Understood. So, yeah, I think that answers. So the summary is most of the times processing the raw feed versus doing certain bookkeeping. I'm calling it bookkeeping activities, but this can be a pre-processing step. Is probably one of the important steps if the AI is supposed to give a desired outcome, right? So in a
Yes.
classical thing, I think earlier we used to do this, and to pre-select the feature, I think very long time back, I had used Bhattacharya distance, right, to pre-select the features once you had not to the beam formation, I guess, but once what is that word here you have mentioned, right? Once the velocity bins were actually calculated, so Bhattacharya distance was actually used to identify whether the person is breathing or not, depending on how much expanded his chest is, expansion and contraction. So just wanted to rehash whether we are still some of these steps are very, very important as a pre-processing step for AI to learn things. Thanks, Gok. That answers. Yeah.
So just to wrap up, here the data out at the output of ADC is actually raw signal because it has no info at all. But once you process the whole thing all the way at the end, this is the end of this presentation. When you get to the end, you complete the pre-processing. But in the AI world, everything starts at this point. So they call it the output as the raw data, since it's not processed by AI. So I need to clarify this. When we say raw signal on a pipeline, it's the input of the pipeline, not the output of the pipeline. And raw means has no info. Nothing is done yet. And back to this file. So here, as I said before, sampling starts immediately after TX shuts off, and it continues until last sample is captured. That's the Rmax. So this is the time axis. You send the pulse, immediately you start sampling the signal, and this is just before the second pulse is being transmitted. Depending on this total sample duration and the sampling rate, say you have L number of samples for the fast time domain, and L is simply the duration in seconds multiplied by the sampling rate in hertz. That's how the fast time defined. And it's called fast time because it's the fastest sampling rate in the radar system. And when we go to the second dimension, we're going to see it's a slower rate. And that's why we call it slow rate. And here in this presentation, we're not going to discuss any heart rate and breathing rate measurements. There we're going to call it very slow time. But it's not a standard classical radar, so it's not included here. So let's find the delayed versions of the transmitted signal using L fast time samples. So that's the next step. And if it's done, we will have the ranges for the targets. And the hardware that does it is called the range correlator. So it finds the correlation between the transmitted signal and the received signal. As normally, for any type of correlation, it gives a peak at the point where the target is. So since the reflected signal is a delayed version of the original, when you take the correlation, it gives a peak at the exact range point for the target. And here you have the ADC data. It's raw, pulses, and channels. We're going to see the 3 dimensions. But here for a single pulse, we have the raw data, and it's going to do the processing and change this ADC signal into range values. And that's very important. And what we do is call this piece as the match filtering. And that's another presentation that will support this presentation. And anyways, the main purpose is range correlator finds the time locations of the delayed versions of the original TX signal. So if you have 3 targets, you see 3 peaks on different time instances. So that's the purpose. So let's see with figures. Assume again, we have a pulse and we receive it, another pulse, we receive it. And if we have 3 targets, we see 3 reflections. And assuming they have the same size, as a function of time, it goes to a further point. So we expect the amplitude to go down, because farther you go, the reflection is going to be weaker. And so let's see. And that's, again, the topic of match filtering. And let's see for the digitally coded signals. Here you go, you see an example, and it's called phase shift keying. So every pulse has a different phase. Here it's binary, so it's -1 or 1. It goes up and down. So you shift the phase, and it's a very basic signal. And most of the digital codes are preferred this way. And you could have other type of signals that we're going to study in digital communication signals. We will see different phase shift keying, frequency shift keying, QAM, and other type of signals, mixed type signals are possible. And the basic idea of match filtering is to multiply the delayed version of this transmitted signal as a reference with the received signal and integrate. And if this transmitted signal, when you shift it, you hit the received signal on the right time, then the integral is going to give us a peak. And it's going to be a perfect overlap with a larger number. And that's the whole idea. Match filter is making original signal, finding its reflection, the delayed version of it. And once you get it, you get a peak. And again, we will need to support this presentation in other presentations that we're going to analyze match filter and also convolution, what the convolution means. But for here, we don't need that much. But the whole idea is, as you see from this figure, the orange is the transmitted signal, and the red is the expected output of the range correlator. So what you have is you're sending probably a very long peak, a very long pulse, because your instantaneous power is limited by your hardware. You cannot go way, way high. But what you can do is you can keep it on for some time so that the energy in this pulse is large. So when you go to the match filter, you multiply it with the same signal and you integrate, and it goes up. And this step is also called pulse compression. So you do pulse compression, and this width is your range resolution. So even your pulse is very long, your correlator will give a peak just right here. And I will show it with some examples, but just to give an idea, for a digital code of length 512, as I mentioned below, the gain is around 54.2 decibels. So it is a huge advantage. Normally, your signal could be minus 100 dB. So you definitely need those gains at each step. This is a standard code. It's called Barker code, and multiple versions and hybrid versions are being used. So here is a good example. You have binary phase shift keying. Plus is sign, let's say minus is minus sign. So it's a waveform. So what you do is you use this waveform and you shift and multiply to the received signal. And at each step, you take an integral and see if that target is there. When your shift hits the target, then the shifted version and the transmitted delayed version of the transmission will hit each other, and you will have a peak of 13. And 13 is 22.3 decibels. That's a huge gain. And your signal will push up, your SNR will improve. And that's a very good step. And that's only 13 dB, you know. And for FMCV signals, you really have very high gains right at the range correlator. You can get even larger values. So again, when you analyze match filters and convolution operation for radar waveforms, it's interesting to see that all generate peak values successfully right at the center of each target. So if you have 3 targets, you see 3 peaks. So no matter what type of waveform you use, you see those peaks. But the thing is, it's not just the peak matters. And here, as you can see, the second figure, this is the output of the correlator. You have some funny side peaks, you know, and you call it the side lobes. And these often create some ghost targets. Think about, you have 3 targets side by side, and the second is very small. So it's going to be confused with the other peaks. So that's a big challenge for radar systems. And in LiDAR, you don't have this problem. LiDAR has its own problems, but if you just talk about the side lobes, that's a big issue for radars. So there's a lot of things going on. And as a radar engineer, it's our duty to minimize those unwanted side lobes. And there are methods, you know, you can improve the radar for this. And it could be simple as multiplication of some vectors or adjusting some radar parameters. If you don't own the radar, you can adjust the parameters. Or if you own the radar, you can design your new waveform and even new scanning modes, they call it. I will talk about it in a bit. So this is the slide that I will skip. This is part of the match filter course that we're going to have. The width of the main lobe is defined as the range resolution. So you give your transmitter, you convol it with the received signal, and you get a peak. And this width defines your range resolution. And the maximum peak on your side gives you the side lobe level. So you want to suppress those side lobes and squeeze this main lobe as possible. And that concludes range processing. So this is the first step. And as I said before, it's the fast time. So the question is, what is slow time? Why is it slow? And what are we doing on the slow time axis? It's a different dimension. So here we have a radar sending a single signal, and it's hitting the target, and assuming target is coming towards us or going away from us. And when this happens, we all know that it's called the Doppler effect. And we have the Doppler processor for this. It started with Christian Doppler, and it goes all the way to Hubble. Hubble stated that our universe is expanding because the signatures of elements coming from stars, distant stars, had shifts, Doppler shifts, and all of them were shifting towards the red. So it was saying our universe is expanding. And you have the same effect even on acoustics. You know, when you have a police car or an ambulance coming towards you, you hear a high pitch. And then right after it leaves you, it goes down. It goes like this. You hear it. The sound immediately changes. That's the Doppler effect. It says, basically, if you have a radar transmitting a signal, and if it hits the target, And if the target is coming towards you or going away, you see a Doppler shift. But unfortunately, this doesn't work for all type of targets. For this, you're not coming towards them, you're not going away. So the radial targets will give you 0 Doppler. And further, these type of angles will make this Doppler shift smaller. So it's not like range processing. It will help you if the target is moving radially. So that's the measured Doppler frequency. And let me see if I have any other notes on this. So here, this is a slow process. We need to somehow measure this Doppler frequency so that we can measure the velocity of the target. And the whole process is done in slow time. And that's the second dimension. Here we have done the range. It processed this data cube. Data cube size didn't change, as you can see. It's the same data, but range is being processed. And the step is basically the FFT of the range data. The whole data is the same size. Then you come to Doppler processing. Once you process it, you play with the second dimension. Again, it's the same data. You play with the same data. And assume that the signal, is narrowband, meaning it's almost like a pure sine wave, exponential. And it means the bandwidth of the signal is much smaller than the carrier frequency, FC. So the reflected signal is not the same sinusoidal sent from the transmitter. It's not only the delayed version of it, but also the frequency is shifted by FT, plus or minus, and we call this the Doppler frequency. So it's roughly velocity of the target, radial velocity divided by speed of light times the center frequency. And this variation is slow. You cannot see it within the pulse. You hit it, velocity is almost the same. So you need to kind of go through the slow time. You take sample, 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 and for each of these samples, each one of them is one axis, and you put this second set of vectors on the side, third, fourth, and you create a whole matrix. And this matrix becomes two-dimensional. One axis is slow time, the other axis is fast time. So we often hear Doppler processing or Doppler filtering. They mean the same thing, but the history is different. So it goes back to the times where the signals were all analog. And FFT, we didn't have any FFT hardware. So when you see engineers say Doppler, today it means FFT. So yes, FFT calculates the spectrum of the signal, and it orders each velocity beam as a filtered version of the original signal. So it is a filter, and it's processing, and simply it's FFT if you do on the digital domain. So let's give a break, just remember that. In the fast time, we sampled the signal for ranges, and it's within the pulse. We just send the pulse, and just before you get the next pulse, you sampled it. It's fast. And then you sampled multiple pulses in the slow time, and you're going to feed it to Doppler processing, and that puts our samples into two dimensions. So this data is called radar range Doppler matrix. And that's very simple. You have the pulses on one axis. Let's say this is the range. This is the first sample. And this is, again, same range, but the second pulse, the third pulse. So this axis is slow. And you call this Doppler bin. So for, let's say there's a target here, you illuminate it with different pulses. So this part of the matrix is for the same range, and it could be a target there. So when you process this axis, we will be able to measure the velocity of that specific target. And if you do the whole matrix, you're going to analyze wherever you have targets you might be looking for a special, target that might be hidden behind the noise. So, and this is, we call the slow time, but some radars will use this as a definition of a single frame. Then they will collect multiple frames, and you could easily call it the very slow time. So every frame is has some slow time, but when you calculate and go for other pulses, then you can do other interesting things. Like for cars, you have LRR, low range radar. You have mid range radar. So you can design a multifunctional radar that operates both of them in multiple pulses. It works, it measures the velocity, and then it shifts its parameters to a different radar, and then it acts like a mid-range radar. Or, you can have multi-frame analysis to measure the heart and breathing rates. That's what we're doing now. And soon we're going to say, hopefully soon, we will develop a multi-scan radar for presence, distance measurement, and heart and breathing rate detection modes, and it's going to be operating per second. So we can have different modes within a single radar. And that's the data. But it's currently two-dimensional. And you have the fast time and the slow time. So if you operate on the verticals, it's a simple FFT. It could be a simple FFT. You have the range processing, and then you go for the Doppler on the horizontal. Then you get the Doppler samples for the same arrangement. So it's very interesting. I find this the beauty of classical radar processing. It's simply beautiful, And if you go further to understand the Doppler processing, for a single range bin, let's say we have a single range bin, single data, you check it for each pulse. You should get the same pulse, right? Because if the target is not moving or not moving fast enough to change the range bin, then you should get the same phase. But this is not what's happening. Even if the radar is within the range, it's moving, before it's going out, you can have some number of pulses within that range. And what you're going to see is the phase is going to be rolling. And this roll is a function of Doppler processing. Doppler, the velocity of the target. So if you have two targets hidden on the same range bin, when you take the FFT, you can separate them. Two targets will be separated. And now you have two targets. And you say targets become resolvable. But what I like to note here, and an important note, that you don't do Doppler processing not just to measure the target velocity, and maybe not just the resolving it, but also you do it that targets become visible. When you do the Doppler processing, you increase the signal to noise ratio of the signal once more. Range detection, range correlation give you some amount of decibels, and here you get another gain here. For example, for a length of 256, that means if you collect data for 256 pulses, which could be very short term, your pulses are very short, you're going with the speed of light, you're waiting for the next pulse just because speed of light is not fast enough. You're waiting. Your first pulse, you hit it. You cannot go very fast because you need to wait for the light to return. And for radar, you see that the speed of light is not that fast. You're waiting. Your electronics is waiting for the light to come back. And let's say you can do 256. That's all you can do because light is slow. Speed of light is slow. If it was super high, then you could have used, thousands within a pulse. But no, it's limited. Speed of light is slow. 256 is not a small number for radar. Then your gain is around 256 makes 48 decibels. So you already had so much gain on the rangeband. Now you're adding another one on the Doppler to be 48. So I think I'm running out of time, right? Srivasan?
Yes, we have 3 minutes to 10:30. So
Okay, so I will speed up. And again, anybody can leave. We will be continuing the recording as a training program. But again, let me go fast to go into beamforming. That's the last process, and I will be done. So Doppler does one axis, range does the other axis, and then you get a peak with two gains, and it's called Thunberg like ambiguity function. So when you do this process, this is your matrix. You see the peaks, and you see the velocity and the range for each target. And for this example, your gain is 102 decibels. And for a car radar, this is so good that it works. You can see a pedestrian at 200 meters. And this is the minimum number that you should get. And it works. Standard processing works. So the last axis is the antennas, right? We have the time axis, fast and slow. That makes us 2 dimensions. And now we're going to have the third dimension. MIMO is multiple input, multiple output. It can be SISO, single input, single output, if you have one transmitter and one receiver. But here you have the transmitters, you have many receivers, and they're located like this, and it creates a virtual array. And we're going to discuss this in a MIMO processing and sparse arrays course. We will have so much to talk about it. And here what you do, I need to at least, talk about it. What is MIMO? MIMO processing simply works when each transmitter sends a coded signal, which can be differentiated at each of the receiver terminals. So here you have 7 transmitters, each having different codes. So for the first receiver, you can differentiate all 7 of them. So what you do is you virtually create 7 different receivers at each receiver. So that makes, total of m times n virtual receivers. That's what it says, And again, that's a topic in our lecture series. So MIMO processing and virtual array concept says if you have transmitters with different codes, and if receivers separate them, you multiply the numbers and you get the number of virtual receivers. So the main take here is that each receiver, we should have m different match filters and m different range correlators, and each of them will separate the signal due to the transmitter. Here we go to beamforming, and that's what it says. You create beams to look for targets in different directions. And the name is not Doppler filters. It's a mistake, copy and paste mistake. It's angle beamforming. So what it does is it uses the same data, range and Doppler is fixed. Then you do processing on channels. You come up with the angles. But normally, this is a huge data. So what you do is after range and Doppler, if target is visible, you just select the targets and then do the angle beamforming just for those selected data. Okay, so angle beamforming, basic facts. Each antenna element has different relative distance to the target. For smaller transmitted signal wavelengths, this distance creates larger phase differences. So for the same amount of phase differences to be observed, you need smaller antennas. And you operate at larger frequencies. And that's what happens. Your frequency increases, your antennas, as you can see, get smaller and smaller for this purpose. And let's continue. One more. Observed relative phase differences are a function of target angle. Depends on the target angle. You observe different phase and your wavefronts are created. Normally, this is very complicated. You have so many values inside square root operators. That is the phase of some exponentials, and it's very complicated. And it's hard to do this integration and processing, and it's a very hot topic in electromagnetics. But this is a problem in the near field, where the target and antenna is very close. And that's the topic of another presentation, near field beamforming. But here, if the target is in the far field, that is sufficiently far, then the whole formulas, full calculations are simplified. And all of a sudden, you see simplified coefficients. And those are multiplication of Fourier coefficients. Again, another topic. It's called Fourier optics. It tells you how you get the FFT. But it's here for us, it's an operation. We already took twice FFT, one for range, one for Doppler. Here again, we have another FFT. And for a uniform linear array or for a uniform rectangular array, it's a simple process. However, if the array is not uniform, like sparse arrays that we're going to analyze, that's special topics on radar presentations. We're going to see that it's not that easy. We will use DFT and some other versions of it, especially when your array is not planar, but conforming to a non-flat surface. Then you have the conformal arrays. That's another topic that we're going to be presenting. So angle beamforming, the objective is collecting different samples from each receiver. That could be physical receiver or virtual receiver. And we measure the phase difference. Phase difference allows us the estimation of angle of arrival of each target. So now we have the radar cube, ADC, pulses, and receiving channels. And then those are fast time, pulses are slow time, channels are spatial, they're sampled exactly at the same instant. And then we calculate ranges, Dopplers, and finally here now, we're calculating the angles by taking FFT. If you calculate target azimuth and elevation separately, then you get detection not in 3 dimensions, but you now have 4 dimensions. So your data cube is 4-dimensional. And if you want to add the amplitudes, then you get the 5th dimension. So some radars say we do 5th dimension. It means we are giving more information. So ADC, you would have very, very low SNR signal. And at each step, your processing gain goes up. And in the first 2 steps, range of Doppler Usually it's sufficient depending on the application. Then you select your target, you select the data, you sparse it, you throw away most of it, you keep probably 10%, maybe less. Then you do the beamforming, only for those selected targets to reduce the computation considerably. But some of the applications, especially in military, if you're especially looking for hidden signals, you don't have this luxury. You have to do the whole processing. So yes, again, it's not Doppler. No, wait. Yeah, again, I was supposed to go jump on this slide. Yeah, sorry. So here is my last slide for the angle beamforming. Here the objective is finding the angle of arrival. So ADC range, pulses, Doppler channels become angles. And so we have the whole processed data in front of us. And as you can see, that's showing us 3 dimensions. As I said in the previous figure, if you're going for azimuth and elevation, it becomes 4 dimensions. So we're done. We see the processing, the whole chain, fast, slow, and we could have very slow times, and which is not just one frame, but you could process multiple frames, and it's called dwell time. You define different operations. You call the mode of the radar. So you could change the characteristic of a radar. It becomes a different radar. Then you call it the multifunctional radar. And for each mode, you call it a scan. So you have scan 1, scan 2. So in radars, you design different scans and you program it, and your code, your radar switch back and forth on the modes. Especially, for example, for the car, LRR, long range, mid range radar can be programmed on a single antenna, a single radar, if hardware allows this. So that's probably, for sake of completeness, I will review the following steps, which is outside the scope of this presentation. So we're done. Beamforming is done. But what we do next is the target detection. And basically, you have you expect a very clean signal because you had 3 different gains applied to your signal. And now your signals should be above the average, above the noise level. And we call it the threshold, right? And we need to think about what threshold means. It's interesting. So threshold is, it's this, it's the straw, it's the grain, what do you call, grain chaff that was used at homes in the history. Homes used to have those type of plants on the floor. And when you have those on the ground, it was used as a barrier at the entrance of houses, of rooms that holds, it's basically grain or straws. The main purpose is insulate, absorb water, dirt, and pets, get rid of the pets, since they didn't have any flooring material in the past. So threshold is the level that we need to cut down the signal and determine where the target is. And you already, you might already know that you have probability of detection, probability of miss. You have 4 type of analysis in probability that we're gonna have a separate presentation for CFAR. So as I said, target detection is done by using a defined threshold. And in radar signals, background noise level often is not constant. So for example, in our MAGIC program, we use range scaling to set this background to a constant number so that we can use detection as a classical method. And however, that constant threshold does not often work all the time. So it should be dynamically calculated often. So it's done to keep the number of false detection almost constant. And this is why it's called constant false alarm rate detector. And false alarm rate is defined by the rate, number of false detection per each pulse and per number, and divided by the total number of range bins. So for each PRI in a fast time for a single pulse, you calculate your false alarms and divide it by the total number of range bins, actually. So normally you do it right after beamforming. So you do the pulse compression, that's range correlation. You do the Doppler processing, then you select which signals, which bins to be analyzed. You do the threshold detection, and there are some different methods. We will see it in those presentations in the future. So CFAR can be implemented in one-dimensional, in 2D, or even higher dimensions, but all are similar. They have the same objective. And the whole objective is the estimation of the background noise in the vicinity of a target. You do have, basically what you do is you keep the target and the neighboring bins out and simply take the average for a defined window. That's all. And when you talk about average, we mean the average, the median, or the middle element of the order statistics. They all mean the same, but give different results. And especially for radar, you need to be very careful because in theory, you always assume that it's normal distribution, Gaussian, but I personally worked in at least for a year, and it's definitely not Gaussian, especially after beamforming. It's wildly different, and that's an important thing. And when, for example, for the BU-MTB case, for the mobility transportation applications, if you have, it becomes very vital. You have to have a very good CFAR implementation. It determines your whole performance for the product, and maybe it will be accepted for 4+ level autonomous vehicle industry, and radar needs to quickly detect and differentiate in milliseconds a pedestrian appearing behind a large bus. So it's a life and death scenario. A pedestrian jump in front of the bus, and your radar might not be picking it because your CFAR is not operating well. So we do have other options, and more details is going to be coming on other presentations. And that's the complete radar processing pipeline. I know I passed my time. I apologize for this, but this is a crucial video for our training program. And this whole process is called RSP pipeline. And normally it's the pre-processing. And some people will be working on post-processing, which includes perception for fall detection, object detection, and etc. So what we hand them, the pre-processing hands them a list of target detections, and we call it the target detection matrix. For each line, you have a target with a defined range, velocity, angle, amplitude, whatever you want to have. So this list of data is our output. And and then usually the object detection is not included in the RSP pipeline. We don't know which one is the actual object. Maybe a person or a car is generating multiple targets. Somebody has to put them together and create the object. So we don't do object processing, object detection. So that's called the post-processing. And the RSP data output often is called the point cloud data. And for for the people who are going to do the post-processing, our output is often referred to as raw data because it doesn't have any information about larger objects. So the object detection is not done. And that's the whole new world, you know, that we're getting into. Probably will not get into perception before summer. We plan to finish up our courses until this summer and hope to see you in your other presentations, and especially thank all for your patience. And let me have any questions if you have. Thanks for joining. Yeah, Srivatsan, you take over.
Yeah, sure. Does anyone have any questions for Gok? Maybe one or two quick questions is okay. Okay, I don't see anything in the chat. And if you have a question, you can also raise your hand. Just checking. Last call for questions.
Yeah, please provide us with your feedback because I really want to know if this presentation was too fast, because it's gonna help our engineers while they're watching the video, because they have right to pause and rewind the video and just do it again and again. So it's going to serve there, but I need to know if I lost some of you. You know, that type of feedback is going to help us, because otherwise I will repeat this over and over again on the other presentations. So let me know. And
Gok, I think Kapil has a question.
yeah, Kapil. Hi, Kapil.
You can unmute.
Yeah, I see your hand.
Yeah. Sorry. Can you unmute again? No. Yeah. No. Issue with unmuting. Can you unmute again, Kapil? I've asked you to unmute again. Yeah. Go ahead.
No. So my question is regarding the match filter. Like you mentioned, by using the match filter, we can suppress the side lobes corresponding to major lobe. So first of all, I want to know like how this works. And in like normal case, in FMCW radar case, we are using very short duration pulse. So if we increase that time, then also we can decrease the side lobes. So then what is the difference between that using match filter and increasing the time?
I think that's a very good question, because it directly takes us to the optimization problem with the radar. Yes, if you take the pulse very long, you have a huge gain on range correlator, because wider it is, the optimization, the match filter integrates more and more, which is going to carry out a lot of energy. So your peak is going to go up. But the problem is, if your pulse is, you're waiting too much, then your Doppler is not going to work. So the longer your range, the shorter your slow down. So you need to optimize it, and that's where the parameter setting for radars work. For example, in TI or Infineon, user needs to define this. You know, how many range bins, how many velocity bins do you want? And you need to pick it wisely. For example, for our BU SSI application, we had a doctor and patients, and we looked at the range, and then we picked up the parameters. But in cabin was different. It was a smaller range, and we were able to shorten the pulse and then have a lot of Doppler gain. So I hope that helped you out, but we will have a different presentation for match filters, range correlation, and convolution operations. So please join whenever we have that presentation.
Yes, sir.
Yeah. Any further questions, including Kapil? Yeah, okay. I mean, thank you all. It's it was a long presentation, but at the beginning I warned you. So hopefully we're not going to have that much long presentations in the future, but we'll see. We'll see. So thanks again.
Yeah, I'll
Thanks.
stop the recording, book. Yeah.
Okay. Yeah, okay. Thanks all.